Hi. Welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University. School of Education, SOE. Postgraduate Certificate in Information and Assistive Technologies for the Instructors of Visually Impaired, PGCIATIVI. MVEI 012 Assistive and Adaptive Technologies. Block-1 Overview of Assistive and Adaptive Technologies. Unit 2 Adaptive Technologies. 2.1 Introduction. Adaptive technology is the name for products which help people who cannot use regular versions of products. Primarily people with physical disabilities such as limitations to vision, hearing, and mobility. Adaptive technology promotes greater effectiveness for persons with functional limitations or disabilities by enabling them to perform tasks that they were formerly unable to accomplish or had great difficulty accomplishing. Adaptive technology provides changed methods of interacting with or enhancements to the technology. Much of cutting-edge assistive technology research begins with mainstream technology that is adapted by AT-oriented designers and software engineers for purchase by service providers for use by children, youth, and adults with disabilities. The challenge is to adapt the most appropriate mainstream technology to convince service providers, who may not be technology savvy, to adapt to the new technology that is based on principles of universal design, UD, that avoids feature creep and is geared to simplicity and optimum end-user utility. 2.2 Objectives. After going through this unit, you will be able to how adaptive technologies are different from assistive technologies. How technologies, adaptive and rehabilitative devices for people with disabilities and includes the process used in selecting, locating, and using them. However, there is a subtle difference between assistive and adaptive technology. Assistive technology means technology developed, designed, existing dedicatedly for differently abled persons. For e.g. Braille-related devices, various types of canes, etc. While adaptive technology includes already existing technology designed by making changes in design, structure, or incorporating add-on components. 2.4 Adaptive technologies for persons with blindness. Some of such technologies are as follows. Computer has been made adaptable. Tape recorders. The major talking book libraries in the country are R.N. Batra Talking Book Library, NAB, New Delhi with support of Media Lab Asia. Talking Book Library, NIVH, Dehradun. M.P. Shah Talking Book Library, NAB, Mumbai. A.N. Kinnarawala Talking Book Library, BPA, Ahmedabad. Pune Blind Men's Association, Pune. Maps and globes. Maps are made adaptable by manufacturing them on vacuum-formed plastic in strong colors with names in letterpress, Maine. Towns by large dots and principal rivers by depressions. Braille symbols denote the names of seas, main rivers and towns and the boundaries on greater than. Political maps are indicated by raised lines. Similarly, globes have also been made adaptive by using tactile technique. Different charts are also available, made up of PVC and employing tactile effect. Vocational devices. Various vocational devices like lathe machine, welding machine, micrometer, etc. explained in previous unit have been made adaptable by incorporating adds-on and other security measures. Speech-enabled daily living aids. Visually impaired persons use many daily living products which has been made adaptable by incorporating speech, such as talking watches, talking calculators, and various talking games. Modification, re-engineering of them. Most of these modifications also make the devices, technologies easy to use for masses. Head-operated pointing devices, eye-glaze pointing devices, mouth, tongue pointing devices, brain-actuated pointing devices, touch screens, voice input systems. Speech-to-text software, voice recognition, voice command software, dictation software, on-screen keyboards, cursor enlargement software, ergonomic, computer-based equipment, etc. Output devices. Computer-based output devices that generally enable blind and vision-impaired persons to use or interact with a computer include Braille display output devices, Braille embosser, printers, screen reading software, screen magnification, enlargement software, large print monitor, etc. Software applications. Different software applications may be adapted by including features specifically designed for users with disabilities. Use of standard menu, commands. Combination. They should rely on more than color to convey information. Availability of installation instructions, user guides, and other documentation in alternate formats, such as large print, Braille, and electronic text is also important. Multimedia products. Multimedia products, which may be distributed on videotapes, or DVDs, pen drive, or the World Wide Web, include synchronized text captions for spoken information and ether audio content, and provide synchronized audio descriptions for visual content. They offer more than one way to input commands or respond to prompts. Or instance. Imagine that a character's voice on a CD tells a child to click on an animal to learn more about it. Children who are deaf or hard of hearing cannot hear the instructions. Children who are blind cannot click on the animal because they cannot see what is on the computer screen. Providing captions in addition to spoken instructions makes it usable by children with hearing impairment. Providing keyboard commands FOI all functions will make it adaptable for children with visual impairment. Captioning and alternative ways of navigating can make a big difference in the ability of students with disabilities to use these technologies independently. Descriptive narration and audio. Navigation, talking menus, are also essential in order to make videos and DVDs adaptable for children with vision impairments. Website SL portals. Website SL portals should be designed to be usable by individuals with a broad range of abilities and disabilities, thus making it adaptable for all. Design, format of information should such that all visitors can navigate the site, access content, and participate in interactive web activities as far as possible. Website SL portals can be made adaptive by provide a text equivalent, typically a description, for all non-text elements, such as audio, video, graphics, animation, graphical buttons, and image maps. This allows those who cannot see the screen to access the information with a screen reader, can read the description of a picture but cannot read the picture. Copy machines. Copy machines can be made adaptable by providing access to it in more than one way, i.e. using keypads, braille keys, touchscreen. Voice recognition EJC. Height and position can be adjusted so that controls are within easy reach and the display can be large to be viewed easily. Document feeders located at desk height, putting them within reach. Similarly, many other tools, devices, aids. 2.6 Universal design. Universal design is the design of products and environments to be usable by all people, to the greatest extent possible, without the need for adaptation or specialized design. The intent of universal design is to simplify life for everyone by making products, communications, and the built environment more usable by as many people as possible at little or no extra cost. Universal design benefits people of all ages and lidies. Universal design is a relatively new paradigm that emerged from barrier-free, or accessible design, and adaptive technology. Universal design strives to be a broad-spectrum solution that produces buildings, products, and environments that are usable and adapted for everyone, not just people with disabilities. Moreover, it recognizes the importance of how things look. For Example, while built-up handles is a way to make utensils more usable for people. With gripping limitations, some companies introduced larger, easy-to-grip and attractive handles as feature of mass-produced utensils. They appeal to a wide range of consumers. As life expectancy rises and modern medicine has increased the survival rate of those with significant injuries, illnesses, and birth defects, there is a growing interest in universal design. There are many industries in which universal design is having strong market penetration, but there are many others in which it has not yet been adapted to any great extent. Universally accessible technology yields great rewards to the typical user as well. One example is the curb cuts, or dropped curbs, in the sidewalk at street crossings. While these curb cuts enable pedestrians with mobility impairments to cross the street, they also aid parents with carriages and strollers, shoppers with carts, and travelers and workers with pull-type bags. People with disabilities must be involved in the design process to make sure that the design is accessible and usable. Universal design is a part of everyday living and is all around us. The undo command in most software products is a good example. Color contrast dishware with steep sides that assist those with visual problems as well as those with dexterity problems are another. Additional examples include cabinets with pull-out shelves, kitchen counters at several heights to accommodate different tasks and postures, and low-floor buses that kneel and are equipped with ramps rather than lifts. 2.6.1 Need of universal design, adaptation. Society is becoming more aware of the needs and limitations of persons with disabilities. The target group includes those born with disabilities and those whose abilities diminish during their lifetime through disease, accident, war, or aging. In addition, the demographic trends like late marriages in metro cities are also raising the prospect of a large number of consumers with decreasing abilities. The serious impact this will have on mass-market products is beginning to be recognized by manufacturers. These developments have sparked increased discussion within the human community on, should the mainstream design of products include consideration of people who have disabilities or are elderly? In other words, should mass-market products be made adaptive via their initial design? In order to find an answer to this catchy and complex question, we may break it into the following component questions. Who are disabled and elderly persons? How large is the disabled and elderly population? Can't the needs of disabled or elderly persons be handled separately or as exceptions? What can the human factors field do for this group? Is it economically and practically feasible to include disabled and elderly persons in the design process for mass-market products? What are the costs? Who are disabled persons? It is important to understand that there is no clear distinction between people who are categorized as disabled and those who are not. A performance or ability distribution for a given skill, ability is generally a continuous function rather than distinctive. This distribution includes a small number of individuals who have exceptionally high ability, a larger number of individuals with mid-range ability, and another longer tail representing individuals with little or no ability. In addition, each aspect of ability has a separate distribution. Thus, a person who is poor along one ability may be at the other end with respect to another ability. The 95th percentile illusion. It should be clear that even if we include elderly and disabled persons in the mainstream design process, it is not possible to design all products and devices adaptive. There will always be individuals who will be unable to use a given product. In order to include a sizable portion of the population in the category of those who can use a product, the 95th percentile data are often used. The problem is that there are no 95th percentile data for specific designs. Rather, There are only data with regard to individual physical or sensory characteristics. Thus, there is 95th percentile for vision, hearing, etc. As a result, it is not possible to determine when a product can be used by 95% of the people. It is only possible to estimate when a product can be used by 95% of the population along any one dimension, since people in the 5% tail for any one ability are usually not the same people as the 5% tail along another ability. It is possible to design a product using 95th percentile data and end up with a product that can be used by far less than 95% of the population. How large is the disabled and elderly population? Determining the exact number of individuals with disabilities or with limitations is difficult. Estimates vary depending upon the definitions of disability. There are also a substantial number of individuals with disabilities who have returned to the workforce despite significant functional limitations and who therefore do not consider themselves disabled. Further data overlaps. That is, the same individual may be counted in both the visually impaired and hearing impaired segments. Therefore, adding the two would give us a false report. Because of the diversity of disabilities, the number of individuals with any one particular type or combination of disabilities is much smaller. This makes it more difficult to accommodate this population in the overall design process. However, even small percentages represent fairly large numbers, i.e., millions, of individuals. In addition, proper design of the human interface, especially of information processing equipment, can help to address the problems of persons with language and cognitive impairment as well. It is interesting to note that the disabled community refers to those without disabilities as TABs, or the temporarily able-bodied. All of us are aging and most of us hope to live to be elderly. If we make it, most of us can look forward to experiencing some type of functional limitations sufficient to make operation of the products in our environment more difficult or impossible. For most, this transition from able-bodied to disabled is a gradual, continuous process. Thus, design for the mainstream that considers the needs of an aging and decreasingly able-bodied population appears particularly worthwhile. Can't the needs of PWDs be handled separately or as exceptions? Although the total number of PWDs is large, each individual disability or impairment area represents only a small portion. We are therefore not dealing with one large group of people but with many small groups. These small groups are further divided by the degree of limitation. Thus, the target user groups are too small to be addressed individually and geographically distributed. As a result, it is both economically impractical and a marketing and support nightmare to design all individual appliances, stoves, microwave ovens, mixers, vacuum cleaners, cars, etc., for each population. This raises a question as to the most effective means of addressing these problems. Is it better to design everything so that it is accessible to most persons, including those with disabilities? Or is it more effective to design for the able-bodied population and create special designs for persons with specific types of disability? Here, therefore, we follow a balancing act. It is unreasonable to design everything so that it can be used by everyone. It is equally unreasonable to produce special designs for each major consumer product to accommodate the different disability groups. Some special aids and adaptive devices will continue to be necessary to fulfill those needs that accessible mass-market design cannot effectively meet. But where mass-market goods can easily be made more accessible through careful and informed design, it appears to be the best and most economical approach. What can the human factors field do for this group? As human factors researchers, much effort have not been directed towards the needs of the persons with disabilities, even though they comprise a large portion of the general population. For example, only a small percentage of the papers in journal have dealt with disability and aging issues, and a scattering of papers have appeared over time. Courses on disability or aging in human factors curricula are rare and usually take the form of special topic seminars. Little or no attention is paid in the standard curriculum to the needs, characteristics, or design considerations to accommodate persons with reduced or diminishing abilities. This lack of focus on those with functional limitations is not because our skills are not applicable to their problems or we are insensitive, although there is room for improvement there. Rather, it seems mostly to be a lack of awareness and a lack of basic knowledge and skills needed to work and teach in this area. Developing this background and expertise would require that we master a much broader range of information. It would also require the development of new areas of knowledge, including the types, degrees, and implications of disabilities and functional limitations, the demographics for these populations, the psychological and economic aspects of disability, and specific strategies for increasing usability of designs by persons experiencing limitations. Is it economically and practically feasible to include PWDs in the design process for mass market products? Experience so far has shown that consideration of disabilities and functional limitations in mainstream design is very definitely feasible from both an economic and practical standpoint. In the majority of cases, accessibility can be added to a product's design for little or no cost. For example, Computer has incorporated several special features directly into their standard operating system to accommodate individuals with various disabilities. One feature, called sticky keys, allows individuals who only have one hand available or who use a head or mouth stick to operate the standard keyboard by using the combination keys sequentially rather than concurrently. Another feature now standard on computers is called mouse keys, which allows individuals who do not have the motor control necessary to operate a mouse to use the mouse keys feature for controlling the cursor on the screen by keys. A third feature is close view, which allows individuals to enlarge the screen image up to 16 times its normal size. Once the features were developed, the cost to include them in the product was essentially zero. Another example of no-cost accommodations can be found on some mass-market mixing bowls. These bowls have small Braille legends cast onto the underside of the bowl, listing the capacity in Braille. Other than a few seconds to cut the dimples into the original mold, there is no additional cost involved in making the bowls. Similarly, some other home appliances manufacturer can also offer Braille tactile overlays for their control panels to facilitate their use by blind or visually impaired users. Accessible design can sometimes decrease costs, in some cases, creating a design which is more accessible can in fact decrease the costs involved in manufacture or maintenance support of a product. One example is to be found in elevator design. Individuals in wheelchairs or on crutches had great difficulty with the large banks of elevators present in many buildings. Often the elevator door would open, but before the person in a wheelchair could get to the correct elevator, the door would close. Therefore, provision of activating the signal tone and light for the proper elevator in advance before its arrival was incorporated. This helped both disabled and able-bodied persons to board the elevator much more rapidly. As a result, it was then possible either to decrease the number of elevators and still provide the same level of service, or to increase the level of service, since the time the elevator is open on a floor reduced. Thus, the more accessible design turned out to be less expensive overall. In general, when products, environments, or systems are made more accessible to persons with limitations, they are usually easier for more able-bodied persons. To use. Some of the potential benefits include lower fatigue, increased speed, and lower error rates. The consequences of not providing accessible designs, the benefits above, are only half of the economic justification for more accessible design. A second, and perhaps more significant economic benefit would be reduction of the costs to society which result from individuals being unable to effectively function independently in the world as it is currently designed. These costs take the form of benefits paid out of tax money for special assistance due to a disabled person's unemployment or non-independent living. In addition, there is the loss to society of these individuals' productivity, meaning loss of tax revenues, creation of wealth, and contributions to society. A number of the persons with disabilities who can and would like to work remain unemployed due to deficiency of adaptive designs. What are the costs? The most significant cost involved in considering functional limitations in mainstream design is that of building the necessary knowledge and skills in our human factors researchers, educators, and practitioners. Before we can include the disability aspects in mainstream research and teaching, we must considerably expand our knowledge base and experience in these areas. This is difficult for most professionals, who already have difficulty keeping up with the literature. In order to include design for persons with functional limitations in our college curricula, we will need to expand the already overcrowded content of our courses and/or add courses to the already difficult coursework requirements for our students. Since incorporating individuals with limitations in our standard design process does not eliminate the need for custom design of special aids, we must also somehow address custom design for disability to cover the needs that cannot be met through more accessible mass market design. Conclusion: incorporating disability considerations in our research and teaching will require substantial effort both as individuals and as a field. Before effectively incorporating disability issues into our curriculum, we will need to better define and refine this area. The basic principles involved in accessible design need to be explored. More specific data regarding the different areas of impairment as they relate to design need to be gathered, condensed, and made available to researchers and designers. Some design guidelines exist, but much more work is needed on basic principles of accessible design. It seems apparent, however, from the demographics and trends in our population, that for an increasing number of the professionals and educational programs in human factors, design for disability must merge with, and become a continuum of, the normal design process. Aside from the significant benefits to society, these efforts should also make our field more robust and lead it into new directions and to new insights. 2.6.2 Principles of the Universal Design. The following principles of universal design to guide a wide range of design disciplines including environments, products, and communications. 1. Equitable use. 2. Flexibility in use. 3. Simple and intuitive. 4. Perceptible information. 5. Tolerance for error. 6. Low physical effort. 7. Size and space for approach and use. Examples: smooth ground surfaces of entranceways, without stairs. Wide, interior doors and hallways. Lever handles for opening doors rather than twisting knobs. Light switches with large flat panels rather than small toggle switches. Buttons on control panels that can be distinguished by touch. Bright and appropriate lighting, particularly task lighting. Auditory output redundant with information on visual displays. Visual output redundant with information in auditory output. Contrast controls on visual output. Use of meaningful icons as well as text labels. Clear lines of sight, to reduce dependence on sound. Volume controls on auditory output. Speed controls on auditory output. Choice of language on speech output. Ramp access in swimming pools. Closed captioning on television networks. Principle 1. Equitable use. The design is useful and marketable to people with diverse abilities. Guidelines. Provide the same means of use for all users, identical whenever possible. Equivalent when not. Avoid segregating or stigmatizing any users. Provisions for privacy, security, and safety should be equally available to all users. Make the design appealing to all users. Principle 2. Flexibility in use. The design accommodates a wide range of individual preferences and abilities. Guidelines. Provide choice in methods of use. Accommodate right or left-handed access and use. Facilitate the user's accuracy and precision. Provide adaptability to the user's pace. Principle 3. Simple and intuitive. Use of the design is easy to understand. Regardless of the user's experience, knowledge, language skills, cognition, or current concentration level. Guidelines. Eliminate unnecessary complexity. Be consistent with user expectations and intuition. Accommodate a wide range of literacy and language skills. Arrange information consistent with its importance. Provide effective prompting and feedback during and after task completion. Principle 4. Perceptible information. The design communicates necessary information effectively to the user, regardless of ambient conditions or the user's sensory abilities. Guidelines. Use different modes, pictorial, verbal, tactile, for redundant presentation of essential information. Provide adequate contrast between essential information and I·s surroundings. Maximize legibility of essential information. Differentiate elements in ways that can be described, i.e., make it easy to give instructions or directions. Provide compatibility with a variety of techniques or devices used by people with sensory limitations. Principle 5. Tolerance for error. The design minimizes hazards and the adverse consequences of accidental or unintended actions. Guidelines. Arrange elements to minimize hazards and errors. Most used elements, most accessible, hazardous elements eliminated, isolated, or shielded. Provide warnings of hazards and errors. Provide fail-safe features. Discourage unconscious action in tasks that require vigilance. Principle 6. Low physical effort. The design can be used efficiently and comfortably and with a minimum of fatigue. Guidelines. Allow user to maintain a neutral body position. Use reasonable operating forces. Minimize repetitive actions. Minimize sustained physical effort. Principle 7. Size and space for approach and use. Appropriate size and space is provided for approach, reach, manipulation, and use regardless of user's body size, posture, or mobility. Guidelines. Provide a clear line of sight to important elements for any seated or standing user. Make reach to all components comfortable for any seated or standing user. Accommodate variations in hand and grip size. Provide adequate space for the use of assistive devices or personal assistants. 2.6.3 Constraints of Universal Design. 2 constraints of universal design are: address only universally usable design, while the practice of design involves more than consideration for usability. Designers must also incorporate other considerations such as economic, engineering, cultural, gender, and environmental concerns in their design processes. Offer designers guidance to better integrate features that meet the needs of as many users as possible. All guidelines may not be relevant to all designs. 2.7 Ergonomics. Ergonomics is the branch of engineering science in which biological science is used to study the relationship between human and their environments. It is basically all about designing the job, equipments, tools, aids, and workplace. Suitable, proper ergonomic design is necessary to Prevent repetitive strain injuries, which can develop over time and can lead to temporary, long-term, or permanent disabilities. Ergonomic research is study of human capabilities in relationship to their work demands. Information derived from these studies contributes to the design and evaluation of tasks, jobs, products, environments, and systems in order to make them compatible with the needs, abilities, and limitations of people. Ergonomics is concerned with a match between human and their work. It takes account of the capabilities and limitations of human beings in order to ensure that task, equipments, information, and the environment suit each person. Ergonomists consider shape, size, color, good contrast, so that a sick person who may have bad vision, due to sinuses, etc., can more easily see. Ergonomics could design the print style, color, and size for optimal viewing. 2. Comfort. Things must be designed in a way that they are as comfortable as possible for most of the users, including those having limited ability. 4. Example: electronics equipments having harsh indicator draw one's eye when surroundings are dark. Ergonomic principles could redesign this based on contrast principles. 3. Ease of use. The things must be easy to use. Street signs, not properly placed, may be difficult to find. This could be addressed with the principles of visual detection in ergonomics. 4. Productivity, performance. The ergonomics also include study of performance. For e.g., different level of sounds at different channels of a television hurts human ears while moving from a low sound level to high sound level. This could be solved by embedding facility of evening out the decibel levels. 5. Aesthetics. The look and feel of the objects is also important, especially while designing for toddlers. Therefore, by taking care of ergonomics, the products can be designed better, comfortable, easy to use, more efficient, and attractive. It is beneficial not only for persons with limited abilities, but for all. 2.8 Unit Summary. In this unit we learnt what the difference is between assistive for persons with visual impairment by incorporating audio,